Welcome to The Explainer. Today we're diving into a phenomenon that absolutely broke classical physics, and really, it reshaped our entire world: the photoelectric effect. So let's get right into it. It all starts with a simple, almost magical observation. If you shine just the right kind of light on a piece of metal, it shoots out a spark of electricity. Seems simple enough, right? But that little spark would end up raising some very, very big questions. For physicists back in the late 19th century, this was just a fascinating mystery. They started collecting clues, trying to figure it out, but the more they found, the stranger the whole thing became. The investigation really kicked off with Hertz back in 1887, but it was Philip Leonard's work that uncovered a set of clues that honestly made no sense at the time. He found 4 really bizarre rules that this effect followed, rules that went against everything they thought they knew. You see, the established law of the land was the classical wave theory of light. It pictured light as this continuous wave of energy, kind of like ripples in a pond, a solid, trusted idea. The problem? When they tried to apply it to this mystery, its predictions were just completely wrong. And here's the first major contradiction. Classical physics basically said a brighter light, a bigger wave, should give the electrons a harder kick, right? More energy? But the experiment showed something totally baffling. It didn't matter how bright the light was. The energy of the electrons stayed exactly the same. The second contradiction was even weirder. The old theory predicted that any color of light should be able to do the job, as long as it was bright enough or you just waited long enough for the energy to build up. But in reality, if the light wasn't the right color, the right frequency, nothing happened. Ever. No matter how long you waited or how bright it was. So the facts were just staring them in the face. The emission was instant, no time delay at all. And these rules about frequency and intensity, they were completely baffling. The old physics rulebook, well, it had to be thrown out. Physics was broken. So how do you solve an impossible problem? Well, the breakthrough actually came from a totally unexpected corner. In 1900, a scientist named Max Planck was studying a completely different problem, and he proposed a really radical idea to solve it. He suggested that energy isn't this continuous, smooth flow. Instead, it comes in these tiny, distinct packets called quanta. Now, the crazy part? At the time, even Planck himself thought it was just a mathematical trick, a gimmick to make his equations work, not a description of actual reality. But he had just accidentally provided the crucial clue. It would take another 5 years and a brilliant young patent clerk named Albert Einstein to see the true meaning of Planck's idea and apply it to this mystery of light. Einstein made this breathtaking leap. He asked, what if light is a stream of these energy packets? He called them light quanta, which today we call photons. And with that single idea, absolutely everything changed. Now, to explain the whole puzzle, Einstein introduced one more simple but brilliant concept: the work function. And you can just think of it as an exit fee. It's simply the minimum amount of energy an electron needs to pay to escape from its home in the metal. And this just illustrates the process perfectly. See, it's not a wave slowly warming things up. It's a series of individual collisions, like a game of cosmic billiards. A single photon hits a single electron, transfers all its energy in one go. The electron uses some of that energy to pay the exit fee, and whatever's left over becomes its speed as it zips away. So the crucial point is this one elegant equation. The electron's maximum speed is just the incoming photon's energy minus that exit fee. This simple formula solves the entire mystery. And look at this. All of a sudden, every single puzzling observation made perfect sense. The threshold frequency, well, if the photon doesn't have enough energy to pay the exit fee, the electron can't leave. Simple. The instant emission, it's a one-on-one collision. Of course it's instant. Everything just clicked into place. The case was closed. But it still needed proof. And this is my favorite part of the story. A physicist named Robert Millikan was, let's just say, he was not a fan of this idea. He set out to disprove Einstein, spent 10 years on meticulous experiments, and, ironically, he ended up confirming the theory beyond any doubt. So why does all this matter to you? I mean, why is this 100-year-old puzzle so important? Because solving it wasn't just some academic victory. It unleashed a wave of technology that defines our modern world. I mean, that basic principle, a photon knocking an electron loose, is the foundation for so much stuff. It's how solar panels turn sunlight into electricity. It's the core of the sensor in your smartphone camera. It's in automatic doors, night vision goggles. It's just everywhere. The photoelectric effect is such a great story because it teaches us that a single revolutionary idea can completely shatter what we think is true and help us build a new world. So it really makes you wonder, what's the next fundamental assumption we all have wrong? Thanks for watching.